Hello, my name is Bob Porter and I'm a consulting SE in Cisco's channel organization. This presentation is the first of 5 which cover Cisco's Data Center 3.0 vision and strategy and the product portfolios that play a part in the data center arena. This presentation is an overview. We discuss the challenges associated with delivering today's data center infrastructure. We will outline Cisco's view of the data center and where the industry is going and why. Then we'll take a brief look at each of Cisco's product portfolios with a data center play and show where these fit.
In considering the challenges involved in building today's modern data center, it's useful to take a look at history and see where we've come from. So going back a couple of decades to the mainframe days, there are a few characteristics that define that. First of all, the compute resource itself, i.e. the mainframe, was in a central location. The data was also in a central location, right alongside the mainframe. Typically the users were local, although they may have had remote terminal access. From the user's experience perspective, things were very static, very character-based, not very immersive. The other problem from the user's perspective was, in terms of getting anything changed, new facilities added, tweaks to code or whatever, it usually took the IT organization quite some time to do that. They usually had to involve outside vendors, for example. So we had a very rigid, very inflexible IT architecture. As time moved on, we moved into more of a client-server environment, and there were a couple of things that drove that. First of all, the advent of cheap PC-type compute resource, alongside the rise of Microsoft Windows, made the IT infrastructure itself easier for the users to use themselves. What that allowed was for the users to essentially develop what they wanted or to use data in ways they wanted in a lot more readily than was in the case in the mainframe days. So what happened was we had a fragmentation of our IT resource. Typically individual departments went their own way, they became their own cost centers, and they also evolved their own support infrastructure quite often. So the advantage there was things became a lot easier, a lot more agile, users got what they wanted a lot more quickly in order to do their job. The con was we started to see significant duplication of not only physical resource but also the support resource, and that of course was expensive. Moving on to the days of Web 2.0, we've seen somewhat of a reversal whereby there's a definite move to consolidate the physical hardware back into a centralized location and the data with it. But in so doing, we've still allowed the users to maintain the control and the immersive user experience that they became used to in the client-server days. Now, there are a couple of drivers to that centralization, one of which I've alluded to already, and that is by deduplicating not only the hardware resource but also the support infrastructure, I can obviously save money. So there's a consolidation piece which equals saving money. The other piece of consolidation is, if you look at the departmental server model, typically the utilization of those servers was very low, say around about 10%. If we assume that a departmental server was $10,000 and we were only using 10% of it, we were wasting $9,000. If we can centralize those servers and drive the utilization up, you can see clearly that you get better bang for your buck and save money that way as well. The other piece to it is centralizing the data, and this has really been driven by the regulatory regime we find ourselves in today. It's become imperative now for organizations to maintain control of the data and hence the applications that are using it also. And in a distributed client-server type infrastructure that we had a decade ago, that was just way too expensive and way too difficult. So two things driving the consolidation into the Web 2.0 world: cost saving and the need for more control. But to emphasize, the users still need and still have got the flexibility that they managed to attain with the decline of the mainframe. Turning for a moment to looking at things from the IT organization's perspective, they're very much being squeezed when it comes to building data center infrastructure, both from a business perspective and an operational perspective. On the business side of things, users are a lot more empowered than they ever used to be. Fewer people working in rigid office infrastructures between set hours. Also, it's human nature for people to want to collaborate, and Web 2.0 has delivered a lot of tools that facilitates that. So basically, users want access to their applications and their data across a much wider time frame than they ever used to. Added to that a lot of organizations are more global than they ever used to be, so their user community or their customer community are spread across the globe. Basically, this means from the IT organization's perspective that any maintenance windows they used to have become smaller and smaller, and in many cases completely non-existent. The other business pressure driving into this too is that of regulatory compliance, which we've already talked about. On the operational side of things, The mechanics of delivering a data center have become tougher too. Power and cooling is obviously a big one, you hear that a lot. Power is much more expensive than it ever used to be and isn't likely to get cheaper anytime soon. Also, organizations are much more aware of what their carbon footprint is and have appreciated the need to do something about that. Asset utilization we've already talked about. That's about sweating the asset and getting more bang for your buck. At the same time as doing all of these things, of course, you have to build an infrastructure that is continually available to meet the business pressures already alluded to, and at the same time defend against security threats which are ever present and ever evolving. So these things all conspire together to make life a lot harder for the IT organization than it ever used to be. So having considered the pressures that IT organizations are under in building a data center, let's see how that translates directly into numbers. So a couple of things to say about these numbers. First of all, they're analyst figures, and the interesting thing about that is if you look hard enough, you can find analyst figures that tell whatever story you'd like. So I'd like to ask you the question, look at these numbers and decide, are they realistic? And by that I mean, are they representative of industry across the board now? Hopefully you'll agree they are. That done, look at them again from the point of view of, are these numbers acceptable? Now there's a different story. Days to deploy an application, 60 to 180. Can you imagine being a manager in Cisco's IT organization and explaining to John Chambers why it was going to take 2 to 3 months to integrate an application acquired through an acquisition perhaps? My guess is he's not going to ask you to do that twice. Jump to storage growth, 40 to 400% is obviously a fairly wide figure there and representative of the fact that storage requirements in organizations are different. If we take Cisco's case, at the back end of our financial year 2007, we had over 7 petabytes of data online, and we're seeing a compound annual growth rate of 50%. So as you can see, a significant cost there in maintaining that. Data center records retention 7 to 10 years, that's obviously driven by the regulatory regime and feeds directly into the storage growth requirements. Now you can't talk about data centers without mentioning power and cooling, of course, and I would suggest the figure of 25 to 30% of overall operational costs is definitely down the low end these days. Power isn't getting any cheaper and it's not likely to. It's interesting too to note that rather than measuring data centers in terms of square feet or the number of racks like we used to, we seem to be measuring them now in terms of power consumed. For example, Google built a new facility in Oregon and that's quoted as a 50 megawatt facility. It's useful to note too that 50 megawatts is the same, roughly, power consumption as 37,500 homes. When thinking about the power, have you ever thought about how much you actually use of that? If you execute 2 searches on Yahoo, you consume the same amount of electricity as boiling a kettle. So think about that the next time you're browsing the web. So overall then, there's definite room for improvement in getting these numbers down, reducing costs and also speeding up the time it takes to do things. So how are we going to do that? Cisco has a vision. Well, it's a vision and a strategy, and we call it Data Center 3.0. Now, that's a Cisco term, but what it seeks to describe is a move that's well underway in industry today already. What's it about? Well, essentially it's 3 things. It's consolidation, virtualization, and automation. And it's our job as IT professionals to provide the means to provide the solutions to our end user customers so that they can achieve that. Why consolidate? Well, we've already talked a little bit about that. It's about sweating the asset, it's about saving money. Okay, give you an example. Within Cisco we now have over 2,000 virtual machines in one of our data centers running on 150 physical servers. And what we saw from a utilization perspective was utilization go from an average of 8% per physical server to 68%. The cost saving associated with that was $14.6 million. So that's the consolidation piece. Virtualization is obviously also a tool for consolidation. Virtualization actually allows us to drive the consolidation deeper than perhaps otherwise would have been the case. The third piece is automation. Automation speaks directly to the need for a business to increase its agility. By that I mean a business's ability to respond to changes in the business environment, be it user demand, supply constraints, whatever it might be. Now, if you've read the book, you'll understand why that's become of paramount importance. And if you haven't read the book, I suggest you do, because it's quite interesting, it's quite scary. We also need to recognize that virtualization and automation are intrinsically linked. And the reason for that is, generally speaking, the more virtualized an environment, the easier or the more readily it can be automated. That said, we also have to recognize there are some definite technical implications or barriers to doing this. If we take VMware's vMotion as an example, in order for a virtual machine to move from one physical host to another physical host, those 2 machines must be on the same layer 2 subnet. So what we have here is a driver that's pushing the size of our layer 2 spanning tree domain to an ever greater size. Now there's some scalability issues associated with that, and there are also some security issues associated with that. Cisco has things such as virtual port channel and Nexus 1000V which directly address those concerns. Let's turn for a moment to the typical IT organization itself. Now what we find here is something of an accidental architecture. It's a very siloed type of thing. We'll find, for example, in most organizations there's a distinct apps team, a distinct security team, a server team, and so on. The amount of collaboration across those teams is not what it could be. Often too it's worse. We see little willingness to share information, and there's very little technical capability within the team in order to share tasks in order to drive a much more service orientated approach. A question you can ask your end user audience is, typically, do you allocate your budget on a fixed asset basis, perhaps a project basis, or is it service based? My guess is most people are going to answer on the fixed asset or perhaps project side, very few on the service based. Ask them too, do they feel there's a gap between themselves as the IT side of the house versus the business side of the organization? How do we address this problem? Well, fundamentally we have to deconstruct the silos that we've seen and move from the silo type approach to a much more service orientated approach. You'll see the barriers between different organizations within the IT infrastructure start to blur and go away. That's certainly happening now between the traditional network side of things and the storage side of things, being driven by fiber channel over Ethernet amongst other things. So basically we need to meld together those silos and make a single fabric, but that fabric is not only from an organizational perspective, it's also very much from a network perspective, and how we do that is through virtualization. We virtualize the network itself, we virtualize the services that run upon it, and we automate our provisioning. We also very much have to deal with layer 8 and 9, the religion and the politics. Overall, the goal here should be that the network is supposed to facilitate the alignment between IT and the business itself. It should be the glue, it should not be the barrier. Let's turn now to the question of 10 gig Ethernet and ask the question, is it really necessary? Well, in summary, the answer is yes, it is, and there are three fundamental drivers to this. First of all, let's look at how servers have changed physically over the years. It used to be that a server stood alone on a floor tile in a data center, or multiple floor tiles even. Time evolved and servers became rack mounted. They evolved a little bit more and they went down to 1U high, then to blades, and latterly into the UCS form factor. The key characteristic across time here is that the density of compute in terms of how much compute I have in a given amount of space has increased very significantly. Add to that, we've gone from single core per processor or CPU to multi-core processors. So the compute density, as I say, in a finite amount of space has increased very greatly. Therefore, the traffic that I need to drive into that space and pull from that space has also increased correspondingly. That's one of the drivers for 10 gig Ethernet. A second is the question of unified I/O. So for those that are new to that, the concept here is I'm going to take what used to be a distinct storage area network and a distinct LAN type infrastructure, i.e. my Ethernet stroke IP world, and meld them into a single infrastructure. Well, if you recognize that fiber channel traffic runs at 4 gig or 8 gig, then the absolute minimum speed I need is 4 gig or 8 gig. So in that context, 10 gig Ethernet is not much of a stretch. Thirdly, and equally important, is that of simple traffic growth. So some numbers here from Quest CTO. What they're seeing on their core network is that traffic doubles every 15 to 16 months. And it's interesting to note that's faster than Moore's Law. On top of that, if they look at it from a per subscriber perspective, this is private broadband subscribers now, the amount of traffic generated or sunk into a broadband subscriber grows by 40% year on year. What that means for the carrier is that the cost per subscriber has to decline by 40% year on year, because I'm assuming that you put yourself in the shoes of a private consumer. You're not willing to pay 40% more next year for your internet service than you did this year or last year. You want to pay the same, if not less. This is fundamentally why service providers are now looking at capping their busiest users. Video is another feeder into traffic growth and a big bet for Cisco. It's interesting to note at the time of writing this presentation that of the US internet population, only 16% are regular users of YouTube. What that suggests to me is there's tremendous possibility of growth of traffic just in video right there. In summary then, the Data Center 3.0 story is all about three things. It's consolidation, virtualization, and automation. Why? We want to save money. How? We want to drive asset utilization higher. We want to centralize everything so we can save on administration and support costs. Why virtualize? Because it's a direct aid and feeder into consolidation, and it can also help increase business agility. How? By decreasing the time it takes to deploy resources. Why? Because agility is everything in the modern business world. So that's the Cisco Data Center 3.0 vision. Let's look now and see how we turning that vision into reality today. Let's consider first the case of unified I/O. What you see here is a typical server as deployed today. The characteristics of it are it has multiple NIC cards to a variety of Ethernet type networks, and it also usually has at least 2 HBAs to a storage area network. So multiple NICs. What if we can take that model and condense it down to what you see on the right hand side, where we have a single connection per server over which we run all of our traffic. Now in practice we'll actually put 2 connections in a given server for simple redundancy purposes. We call these NIC cards converged network adapters. Why would we do it? Simple, save money. Cisco recently completed a data center in Texas. Now unfortunately that was designed without unified I/O in mind, but somebody did sit down and analyze what we would have saved after the event. In the case of simply cable infrastructure, the company would have saved between $1.5 and $2 million. We would have reduced our overall power consumption by 8%, a very significant figure in a data center. Our savings on network infrastructure would have been between 20 and 30%. That saving would have funded our server growth for the next 12 to 18 months. So very real, very tangible savings out of unified I/O. A key component in unified I/O or in delivering that is the Nexus 5000 family. This is the first to market switch that offers the ability to run fiber channel over Ethernet directly from a server into the network infrastructure. Characteristics of the 5000 are it's a 10 gig Ethernet switch designed for top of rack or potentially end of row, extremely low latency, and very extendable in the case of using the Nexus 2000 as virtual line cards. Let's look at the CNA or Converged Network Adapter. This is a very simplistic diagram that shows what this thing is conceptually. Basically we have a single cable connection coming out of the card into the network infrastructure, but presented to the operating system is a distinct Ethernet connection and a distinct fiber channel connection. If you were to go into the system properties on a Windows machine, for example, under the network side of things you would see a NIC card, and under the rest of the system you'd see a SCSI adapter. So this is transparent to the operating system. So let's turn now and look at another member of the Nexus family and see how we can address the issues arising out of server virtualization. So as we discussed earlier, one of the problems introduced by vMotion is the ever-expanding layer 2 domain. Why do we have that problem? Well, basically any physical machine that's a candidate for running a given virtual machine has to have common network connectivity with its peers. In other words, if a particular machine, virtual machine that is, requires VLAN 101, we have to provision VLAN 101 to every single physical host which might run that machine. A second problem is it's impossible to view or apply policy to locally switch traffic within a physical host. So that means we don't have visibility or control over traffic which moves from one virtual machine to another within a physical host. Thirdly, and equally importantly, is the need for collaboration between the network folk and the server folk. Traditionally something that's been difficult to achieve simply because of the lack of understanding that one has into the other's world. So a layer 8 problem. What can we do about that? Well, introducing Cisco 1000V. This is the industry's first third-party virtual distributed switch. What you see here is the VMware network model, if you like, prior to 4.x, whereby we have a virtual switch in every ESX hypervisor on every server. What we do now in the 1000V world is first of all replace the VMware virtual switch with a Cisco virtual switch. The next step is to consider each of those virtual switches a distinct line card, but part of the same logical whole. That makes a distributed virtual switch. And a distributed virtual switch is controlled by a virtual supervisor module. Then what we do is we hook the virtual supervisor module via an API up to VMware's virtual center. So now when a virtual machine is going to be moved under the control of vCenter through vMotion, vCenter can signal to the VSM that that's going to happen, and the VSM can take the appropriate network provisioning steps. What this allows us to do is give each virtual machine a distinct network personality that follows it through the data center. And the characteristic or constituent parts of that personality are, as you can see here, the VLAN ID, any quality of service requirements, any rate limiting we might want to put on, any security constraints, and also the ability to mirror ports out of the physical machine to a remote monitoring station. Now what we can do is, as a virtual machine needs to move from one server to another server, its network policy can follow it. And it's the job of the virtual supervisor module to ensure that the destination virtual Ethernet module on the destination ESX host is provisioned ahead of time as vMotion occurs. Logically, this is what a 1000V system looks like. As you can see in the diagram here, we have two virtual supervisor modules, so we do have the concept of active and standby, and a number of virtual Ethernet modules or line cards, up to 64. So we can have up to 64 physical ESX machines part of the same distributed virtual switch. Here you can see the Nexus 1000V in the context of the wider Nexus portfolio. The 1000V then is a software virtual switch which resides inside the ESX hypervisor. At the access layer we have the Nexus 5000 series, and at the aggregation or core layer we have the Nexus 7000 series. The Nexus 5000 is a layer 2 top of rack switch offering an extremely low latency of only 3.2 microseconds. There are two flavors, the 5010 or the 5020. Offering 20 ports or 40 ports fixed and 1 or 2 expansion ports respectively. The expansion ports are used for either Ethernet connectivity or fiber channel connectivity into the storage area network world. The Nexus 2000 is a remote line card which connects to the 5000 parent and offers high density 1 GE server access. The Nexus 7000 layer 3 switches come in two flavors, the 7010 or the 7018. The 7010 offers 8 slots and the 7018 16 slots, each of which is rated at 230 gig per slot. That allows a 5018 to be deployed with up to 512 ports of 10 gig Ethernet at an oversubscription ratio of 4:1, or 128 ports of 10 gig Ethernet in a non-blocking configuration.
Let's turn now to UCS. Cisco's Unified Computing System, or UCS, takes commodity x86 components, Intel's Nehalem processor, standard memory DIMMs, disk drives and so on, and builds on that, adding Unified I/O technology as introduced in the Nexus product line, plus some more Cisco secret sauce which we'll discuss in the next couple of slides. All of these components are blended together into a single system, having a single management entity in order to deliver something that goes beyond a simple blade server solution. Here you see a server blade, or what I'll call a compute blade, and we'll see why I make a distinction between server and compute blade in just a moment. We need to connect the compute blade to both an IP network and a storage area network. This is achieved using an Ethernet NIC and a host bus adapter connected to the LAN and SAN respectively. Within the UCS system, this connectivity is achieved using Unified I/O technology in basically the same way as the Nexus 5000 and the Nexus 2000 systems. Here you see a fabric interconnect, which is analogous to the Nexus 5000, and a fabric extender, analogous to the Nexus 2000. A full UCS deployment has two fabric interconnects and multiple fabric extenders, 2 per chassis. The first secret source component beyond Unified I/O is the network adapter present on each compute blade. Shown here is Cisco's Paolo mezzanine adapter. Paolo is seen by the operating system or hypervisor as a configurable number of distinct PCI cards, both Ethernet NICs and HBAs. Up to 127 cards can be presented to the operating system. The UCS system has to track each of these logical connections, apply appropriate quality of service parameters and so on. In order to achieve this, UCS uses virtual network tagging, or VNTag. Simply put, a VNTag is the interface cable between a logical interface provided by Paolo and a logical switch port it's connected to, either fiber channel or Ethernet, in the fabric interconnect. The next secret source area is server profiles. A traditional server, be it a standalone server, rack mount or blade, has an identity. Actually, it's got several identities. These are its universally unique identifier, or UUID, plus one or more Ethernet MAC addresses and one or more fiber channel worldwide names. Note too, associated with the hardware providing these, there will also be embedded firmware. Next, a server has all sorts of configuration parameters. On the storage side, the server may utilize direct attached storage and/or require SAN connectivity, so there's a raft of configuration data associated with this side of things. On the network side of things, most servers have multiple Ethernet NICs, each with a MAC address, perhaps multiple VLAN configurations, perhaps with specific speed and duplex settings as well as the associated firmware versions. In UCS, all of this identity and configuration information is encapsulated into a server profile. A server profile defines the very identity of the server. UCS applies service profiles to compute blades to turn a hardware blade into a server. This is why I drew the distinction between a compute blade and a server in the previous slide. A blade is a compute blade until a service profile is applied to it. At that point, it becomes a particular server. A service profile is another layer of abstraction within the UCS system. Profiles can be moved from blade to blade or duplicated as circumstances demand. All state information is associated with the profile, not with the hardware blade itself. Let's turn now to the problem of memory. Many of today's workloads are not gated by CPU power, but rather they're memory bound. This problem is compounded by multi-core high-performance CPUs and virtualized server environments. A second consideration is the fact memory pricing is non-linear. Doubling the capacity of a DIMM certainly does more than double its price. The slide shows a typical dual-socket Nehalem blade. Typically, fully populating such a blade allows for 144 gig of memory, but with reduced memory clock speed, or alternatively, a maximum of 96 gig of memory at full performance. With these considerations in mind, Cisco has developed and patented an extended memory technology to address these problems. A Cisco ASIC sits between the Nehalem's memory controller and the memory subsystem, essentially acting as a proxy. This ASIC allows 4 real DIMMs to be seen as a single DIMM by the Nehalem controller. This means 48 DIMMs can be deployed with no downgrade in memory clock speed, given a maximum of 384 gig of memory per blade. That said, this technology also delivers a benefit where such a large memory footprint just isn't needed. Now a given memory requirement can be met by utilizing a larger quantity of smaller capacity DIMMs, and so achieving a significant cost saving. The final key characteristic of the UCS system is on the management side. All of the features and benefits I've described are managed through a single management entity. A typical UCS system consists of multiple chassis connected to 2 fabric interconnects. Each of these fabric interconnects is always actively passing network traffic. Embedded in each is the UCS manager, which behaves in an active standby configuration. The UCS manager controls the entire system. On the hardware side, that covers adapters, blades, chassis, fabric extenders, and the fabric interconnects themselves. On the software side, UCS manager looks after service profiles, so all the configuration items a profile encompasses, as well as the upstream network configurations. From an administration standpoint, full role-based authentication and control is provided, along with multiple interfaces to external management and monitoring systems such as IPMI, SMASH-CLP, XML, SNMP, and so on. In summary then, Cisco's UCS is much more than a simple blade system. It adds new virtualization technologies, unified I/O, VN tagging, service profiles, to x86 compute, while also significantly increasing the available memory footprint. The system offers a single management touchpoint, which does all the provisioning work needed to prepare a compute blade, providing its server identity and configuration, as well as LAN and SAN personalities, right through to the egress point of the UCS system at the fabric interconnect.
Let's turn our attention now to the world of storage area networks and consider virtual SANs. Cisco's approach to fabric virtualization is to allow one physical fabric to be split into multiple virtual fabrics. This is somewhat analogous to the world of Ethernet where we use VLANs, but with one key difference. In Ethernet we take a physical port on a switch and we segregate it into multiple logical virtual LANs. In the vSAN world, a physical port on a switch or a director belongs to one vSAN and one vSAN only. So the segregation is done more at the director or switch level than it is at the port level. The idea is that we can run multiple SANs separately from one another on a common infrastructure and thereby save money. Instead of each department having its own SAN with the associated overhead that entails, they can consolidate onto a single one. In the case of Cisco, we saw our storage utilization increase from around 20% to 66% through implementing vSANs. And that led to an overall cost reduction from 21 cents per megabyte down to 1.2 cents per megabyte over 6 years. We also calculated over the last 3 years alone we've saved $60 million in cost avoidance, i.e. negating the need to buy further SAN infrastructure. A little more detail here. This graphic shows an MDS 9000 split up into multiple vSANs on a per port basis, as I mentioned. An important note here is within the context of a vSAN, all the fabric services are completely isolated from other vSANs. So if for any reason there's some disruption to the fabric services from a fiber channel perspective, that disruption is localized to a particular vSAN and does not affect the others. Let's turn our attention now to another area of the data center and look at ACE, the load balancer stroke content switcher. What I'm showing you here is actually an infrastructure for remote desktop connections based on VMware's View product. Basically what happens here is our remote users form incoming requests for service to a VDM or virtual desktop manager connection server. That connection server is essentially the broker between the user and the ESX servers running the virtual desktops. Now, as we need to scale our user community upward, the traditional approach has been to add further VDM connection servers. The problem with this is we now essentially have three different user communities represented by our green, our red, and our orange. To achieve scalability, we have to provide three different URLs or IP addresses out to the user community and manually essentially balance which users connect to which VDM connection server. That's doable, but it's not very elegant. A further problem arises should a VDM connection server fail. Now my green users have lost connectivity. The only way to get connectivity back to a virtual desktop is to have them manually switch the URL they're using for the VDM connection server. Not particularly elegant. The solution to this problem is to drop an ACE load balancer ahead of the VDM connection server. What the ACE load balancer is going to do is automatically balance the incoming requests from the remote clients to the VDM connection server, which will in turn balance the requests out to the ESX servers providing the hosting services. While the ACE load balancer is doing this, it can make intelligent decisions as to which VDM connection server should serve a particular user based on the current best response time from that server farm. The other thing it'll do on a dynamic basis is monitor the health of the server such that should a server fail, any new incoming requests will be balanced across the remaining healthy servers. So all of this is done using one URL published on the ACE external interface, and any changes made on the back end are all transparent to the users, so they continue to use the same URL, the same settings as they always did. A key feature of the ACE product that's directly pertinent to the Data Center 3.0 story is that of virtual device support. The concept here is a single ACE unit in terms of hardware supports multiple virtual devices. So now as needs evolve and applications are added to the infrastructure, rather than deploying physical ACE units, I can instead deploy a new virtual device. This saves purchase time, it saves install time, and overall saves management. What's virtualized here is not only the configuration from a setup perspective, but also resource within the unit itself, so throughput, memory, and CPU cycles are virtualized. On top of that, within each virtual device, there's full role-based administration control. In terms of the limits of the number of virtual devices, we support 5 by default with no extra license needed, and then up to a maximum of 250 for the ACE module for the Cat6K, and up to 20 for the ACE appliance. This speaks very nicely to the redundancy model 2, whereby we have 2 ACE units, each of which have multiple virtual devices, set up such that for any particular virtual device, it's active on one unit and is in a warm standby mode on the other unit. So it's a 1+1 redundancy model there. A further use of ACE is in virtualizing our network infrastructure. What we can see here is a typical enterprise network where we have multiple server farms, perhaps for different functions or belonging to different departments. Rather than replicating that infrastructure from a load balancer perspective over and over, what we can do instead is collapse each of those load balancer tiers down into a virtual device context on an ACE load balancer and have either a single ACE unit or usually 2 for redundancy serving our multiple server farms. We can extend that idea too to that of the enterprise network where there are multiple tiers of services, perhaps front-end servers, application servers, and then back-end database servers. Again, rather than deploying a set of load balancers for each tier, we can instead deploy one pair of ACE units and use virtual devices to serve each server farm in turn, again with complete virtualization and complete separation of control and complete separation of administration. This slide shows the overall ACE product portfolio and is included for the sake of completeness. So the ACE units I've shown you in the context of VMware View and also virtualizing our network infrastructure is the appliance and the modules that you see in the center part of the picture. Also included in the ACE product portfolio is a web application firewall and an ACE XML gateway. Then, on a slightly different flavor, we have our ACE GSS, which is a global load balancer, offering the ability to load balance incoming requests using DNS techniques across multiple data centers, and in fact across multiple data centers across the globe. Let's turn our attention now to the area of WAN optimization and Cisco's WAS solution. So we have now a barrier to consolidation, that being the wide area network. Traditionally, users have interacted with servers that are local to them, where certainly we've had plenty of bandwidth and virtually no latency. They may have had the odd ad hoc request to a remote server, but that was very much the exception. The problem is, in seeking to consolidate all of our servers from the branch locations into the central data center for the reasons we've been discussing, our traffic pattern has now changed, whereby all of our users' traffic now needs to traverse the wide area network, where of course the bandwidth available to us is substantially less than the local area, and the latency involved in sending that traffic across the network is substantially higher. So the WAN has become a bottleneck. To address that, Cisco's developed the wide area application services. Now, to deploy that, we essentially put a WAE, a wide area engine, at each branch location, and these work as peers to one another to optimize traffic going across the wide area network. So this is a symmetrical type solution. In order to optimize the traffic from a particular branch, I do need a WAE both sides of the WAN link. To address the needs of mobile users, we have WAS Mobile, which works in a very similar way, but is available to Windows users as a piece of software which runs on the laptop to substantially increase the speed, the application response time over the internet and a VPN, and in particular over mobile radio networks where packet loss and latency is a particular issue. Let's take a brief look at how Cisco's WAS works. So WAS will accelerate any TCP-based application across the wide area network. The first technique we use is TFO, or TCP flow optimization, which in summary is the manipulation of TCP segment numbers, sequencing and acknowledgements such that we can achieve the best possible throughput across a high latency, low bandwidth link. The second type of technique we use is compression. DRE, or data redundancy elimination, is a Cisco proprietary technique whereby peer units build a dictionary of data that they've seen before, such that if they need to send that data for a second or subsequent time across the WAN, they can instead send a smaller dictionary entry. In best possible case, we can substitute a 5-byte dictionary entry for up to 16K of data. LZ compression is used for on-the-fly compression across the wire for either data that we haven't seen before or indeed for those dictionary entries. The third type of optimization are application optimizers, or AOs. An AO is a software construct for a particular protocol that essentially intercedes or proxies in the communication between the client and the server. For example, we have a MAPI AO which understands the protocol exchange between an Outlook client and an Exchange server and is able to intercede in that communication and accelerate the traffic. We also have application optimizers for CIFS, for Windows Print, for HTTP, SSL and NFS. Cisco WAS can also provide services for the remote office using virtual blade technology, which I'll talk about in just a moment. WAS offers multiple deployment options. There's the WAE, or the appliance. There's also the NME, which is a module that fits into Cisco's ISR router platform and offers a particularly attractive and cost-effective option for branch deployment. From a network integration perspective, we can go inline where the unit is transparent to the layer 3 infrastructure, or we can go out of path using policy-based routing, or WCCP, which has the advantage of both offering scalability and also resilience options. Finally, WAS integrates closely into the Cisco infrastructure overall. A key feature of WAS, in contrast to the competition, is we don't change the IP address header information in terms of either the IP address or the port numbers used, and so remain transparent to firewalls, to instrumentation such as NetFlow and MBAR. Our final slide shows Cisco's WAS portfolio. Units are designed to meet wide area bandwidth requirements for T1E1 in the case of the NME modules and the Wave 274, right through to the 7371, which is able to saturate a 1 GE WAN link. Remember too that through the use of WCCP, further scalability and resilience can also be achieved. The three NME modules bottom left fit Cisco's ISR router platform and are particularly cost-effective for branch deployments. Lastly, those units having the Windows logo behind them are the ones which are virtual blade capable appliances.
In summary then, the Data Center 3.0 vision is about three things: consolidation, virtualization, and automation. The aim is to save money and at the same time increase business agility to meet the dynamic demands of the modern globalized business environment. We have looked at Unified I/O, the Nexus product line, and how that fits with server virtualization. We have taken a glimpse at the SAN world. We've looked at the unified compute system and seen just a couple of the new innovations that brings to the server world. We've seen how ACE not only provides load balancing and content switching services, but also can virtualize network infrastructure. And finally, where wide area network optimization fits as a key enabler into the consolidation piece. Thank you for watching.